Welcome to my video course on engineering FRMCS. It's fantastic to have you all here. So, today we're tackling something absolutely crucial in modern railway communications: managing network congestion. You know, when we're engineering the transport stratum for these 5G rail networks, we really have to plan for those moments when the system gets pushed to its absolute limits. So how do we guarantee that life-saving, mission-critical data gets through no matter what? Well, let's dive into exactly how we make that happen.
Here's our syllabus and roadmap for today's lecture. We're going to start by looking at how we manage radio frequency congestion, and then we'll define our ARP mechanisms. From there, we'll break down the 3 core ARP parameters, look at how we configure values 1 through 8, and finally, walk through how to execute preemption successfully before we wrap things up.
Okay, Section 1, Managing Radio Frequency Congestion.
Right off the bat, as engineers, we're up against a fundamental physical limitation. Radio frequency bands are finite. They can and do get congested. So I want to ask you, what actually happens when radio resources are scarce? Picture a scenario where you've got high-speed trains, trackside applications, automated systems, and critical voice services, and they all suddenly demand bandwidth at the exact same time. When that network load hits its peak, how does the system choose who gets to talk and who has to wait?
Well, across the end-to-end quality of service path, we have to remember that not all communications carry the same urgency. I mean, an automated train control signal, that is objectively more critical than a routine data log from a maintenance sensor. Because of this, we need a highly dynamic prioritization framework. This framework is what ensures that our absolute most critical railway operations always get precedence when bandwidth gets tight. It's how we enforce that strict quality of service to guarantee congestion-free communication when it matters most.
Moving on to Section 2, Defining ARP Mechanisms.
All right, please take note of this definition, as it's the foundation of everything we're discussing today. Allocation and Retention Priority, or ARP, is a 5G quality of service mechanism used when resources are scarce to decide which communication has precedence for resource allocation at any given time. In an FRMCS environment, ARP is the ultimate boss. It's the definitive decision maker that dictates the hierarchy of every single data packet trying to squeeze through our network.
A really helpful way to visualize this is to think of the network as an emergency room triage. Just like in a busy hospital, our network has to continuously assess the severity of all incoming traffic. And sometimes the doctors, which in our case are the network control functions, well, they have to make some pretty tough choices to clear a bed for a critical emergency. Less urgent tasks simply have to be set aside so that life-saving critical communications can take immediate priority.
That brings us to Section 3, the 3 AR parameters.
Now, ARP isn't just one single magic number. I want you to pay close attention here because it's actually a 3-part framework. The 3 components are priority level, preemption capability, and preemption vulnerability. These 3 parameters are constantly interacting behind the scenes to manage the quality of service flow across the entire railway network.
Let's unpack the first parameter, priority level. This basically defines the relative priority of a given quality of service flow. But here is a slightly counterintuitive engineering rule you absolutely must remember. The flow with the lowest numerical value is actually the one that receives the highest priority. So a priority level of 1 completely outranks a priority level of 5.
The second parameter is preemption capability. This one asks a simple question: can this specific flow take resources away from others? Going back to our ER triage metaphor, this tells us whether the network is authorized to pull a less critical patient out of their bed to make room for a new high-priority emergency. If a flow has this capability turned on, it can forcibly grab resources that were already handed out to lower priority flows.
And the third parameter is preemption vulnerability. This one asks the opposite question: can this active flow lose the resources it currently has? Basically, it dictates whether a flow that's already running on the network can have its resources yanked away and reassigned to a newer, higher priority flow that just showed up. It's really just the flip side of the capability parameter we just talked about.
Let's apply this in Section 4, configuring values 1 to 8.
So how do we configure this in the real world?
Well, the rules for the FRMCS transport stratum are incredibly strict. The system is explicitly mandated to use ARP values 1 through 8, period. That ensures we have standardized prioritization across all rail networks for mission-critical operations. Meanwhile, values 9 through 15, those are left open, reserved as a national matter so individual countries have some flexibility for their other non-critical implementations.
And just to drill in that golden rule we discussed a minute ago,
The number 1 represents the absolute highest priority you can possibly have in this configuration. If a session is tagged with an ARP value of 1, it has the power to execute preemption over all lower priority levels, meaning everything from values 2 through 8.
Now you might be wondering, where exactly does all this intelligence live? Well, the configuration and mapping of these ARP values are handled by the 5G policy framework. Specifically, it's the Policy Control Function, or the PCF. The PCF acts as the brain here, evaluating the session category of the communication to authorize these specific ARP parameters based on our strict network rules.
All right, Section 5, Executing Preemption Successfully.
Let's put the theory and configuration together and walk through the chronological steps of how preemption actually executes. Step 1, the network detects the congestion or resource scarcity is happening. Step 2, a new incoming communication arrives, and the system immediately evaluates its priority level. Again, that's going to be a number from 1 to 8. Step 3, the system cross-checks the preemption capability of that new incoming flow against the preemption vulnerability of the flows already running. And finally, Step 4, if it's authorized, those lower priority resources are freed up and instantly reallocated to our critical incoming communication. It's a very precise, linear process.
But before we wrap up, I do need to add one crucial nuance. While ARP is fantastic at handling the active flows inside the network, we also rely heavily on something called Unified Access Control. This operates right out at the device edge. It helps prevent overload by barring low-priority mobile-originated requests before they even get a chance to hit the core network. So it manages those high-load scenarios right at the source, which sometimes means preemption isn't even necessary.
And finally, Section 6, Lecture Conclusion.
If you take away just one single concept from today's lecture, let it be this core principle. The ARP framework, specifically configured from 1 to 8, is what guarantees that when our network is pushed to its absolute breaking point, our mission-critical rail communications will never fail. It is literally our definitive safety net against radio frequency congestion.
But you know, that does leave us with a pretty fascinating engineering challenge to think about for next time. What actually happens when these quality of service requirements dynamically change mid-journey, say right in the middle of an active session? Well, that's exactly the scenario we're going to dive into in our next module. Thanks again. See you next video.